This is the microscope. These are where our detectors are. There is actually a microphone on this thing, I think. This is a screenshot of the control software. This is Dr. Guillaume Lessard. Okay, so we'll start it. And we'll tell it to save the data. Okay, and now we're acquiring three-dimensional trajectories. Wow, this is fantastic. And this is just a simple sample holder, conventional optical microscope.
Yeah, our droplet is just under here.
Yeah. And now we're following trajectories of individual quantum dots.
The following are a handful of selected three-dimensional trajectories of individual quantum dots, followed with the 3D tracking microscope in a glycerol water mixture. The opening screenshot lists the trajectory number and the duration of the trajectory, as well as some other experimental parameters, such as the excitation laser power and stage feedback rate. These parameters, with the exception of the track duration, are the same for all of the trajectories included in this DVD. In this first trajectory, we follow the Brownian motion of an individual quantum dot, diffusing in 3 spatial dimensions for approximately 24 seconds. The counts seen on each of the 4 photon detectors used for feedback are shown to the right. Ideally, each detector should see an equal count rate while tracking. This next trajectory lasts for approximately 4 seconds. While shorter in duration than the other 2 trajectories shown in this DVD, this movie emphasizes and showcases the speed of the quantum dots we are tracking. We need to update our stage position 200 times each second in order to follow this type of fast, diffusive behavior. This is the last trajectory we are showing. In total, we collected over 1,000 trajectories this day and have selected a few of our favorites for this DVD. We follow this quantum dot for 32 seconds. This trajectory is interesting in that one can see the counts on each of the 4 detectors start out low, approximately 100 counts per 5 milliseconds, and then rise rapidly to a value closer to 300 counts per 5 milliseconds. This shows we can acquire a quantum dot skirting the edge of the optical probe volume and place it closer to the dead center of the laser excitation beam.